So let us continue our solutions of field theory problems. We already know what an algebraic number is. An algebraic number is a complex number that satisfies a non-zero polynomial with rational coefficients. Now, an algebraic number will be called an algebraic integer if it satisfies a non-zero polynomial with integer coefficients. Okay, that's a special type of algebraic number. So based on this definition, we then have this exercise. It is given that A is an algebraic number. We have to prove that there is a positive integer n by which if we multiply A, then the product in A will be an algebraic integer. So let us see the solution. Since A is an algebraic number, there exists a polynomial in the polynomial ring over the field of rational numbers such that A satisfies this polynomial. And in fact this is nothing but f of A that is equal to 0. We know that algebraicity of a complex number implies that there is a non-zero rational polynomial that the number satisfies, but we have already seen that it implies that there is one such non-zero monic polynomial that also the number satisfies. So we are using that fact here. Okay, so there is a monic polynomial with whose coefficients are rational numbers such that A satisfies this polynomial. Okay, now multiplying the above equation by a suitable integer, we get beta m plus beta 1a. Now it won't be beta 1, it will be beta m minus 1 a plus beta 1 a to the power k minus 1 plus beta naught a to the power k equal to 0, where are integers and beta naught is greater than 0. How is it possible? To see this, let us take one concrete example. Suppose the equation that we have here looks like this: a to the power 4, say k is 4, alpha 1. Since all the alphas are rational numbers, so they will be quotients of integers. Suppose 2 divided by 3 a cube minus 1 divided by 5 a square plus 16 divided by 11 equal to 0. So this is our alpha 1, alpha 2 and alpha 3. Okay. Will it be alpha m? Where is m coming from? It will be alpha k. So this is alpha naught, alpha 1, alpha 2, alpha 3 and alpha 4. Okay. So we don't have that term involving a. So this is alpha 1, alpha 2 and alpha 4. So I was getting confused that this is alpha 3. Okay, fine. So suppose our this equation looks like this. Now what we are saying? We are now saying that we can multiply this equation by some, I seem to be not writing the t's properly. Anyway, so we should be able to multiply this equation, both sides of this equation, by a suitable integer, so that the resulting equation has only integer coefficients, not rational coefficients. To see that, you just have to multiply this equation by the LCM of the denominators in these rational coefficients. So in this case, the LCM is 3 times 5 times 11, 15, so 165. So if you multiply by 165, you get this 55 times 2 minus 33 a square plus, so this is 15 into 15 times 16. So this is again a polynomial that a is satisfying, and it has only integer coefficients, and besides that the coefficient of the largest coefficient of the term which has the largest exponent is positive. We can conveniently choose the things so that it becomes positive. In these rational coefficients, even when the rational number is negative, for example, we have here, the denominator can always be chosen to be positive, keeping the minus sign with the numerator. So when you have all the denominators positive, their LCM is a positive integer. We will consider the positive LCM and multiply the equation by that. So this is our, the way we are writing things, this is our beta naught a to the power 4 plus beta 1 a cube plus beta 2 a square plus beta 3 is 0 plus beta 4 equal to 0. So beta naught is 165, which is positive. Beta 1 is 110. All these are integers. Beta 2 is minus 33. That is fine. The other integers can be negative. That's allowed. And beta 4 is 240. So multiplying the above equation by a suitable integer, we get this, where the coefficients are all integers and the one in the highest degree term, the one with the highest degree term is a positive integer. Now what we do, we will now multiply both sides of this final equation by beta naught to the power k minus 1. Note that this k is positive. In fact, should we mention it here? Polynomial belonging to k of positive degree k such that f of a is equal to 0. Okay. But what is the justification for taking the degree of this polynomial to be positive? That is, why is it the case that k has to be positive? If you are unable to take k positive, then k must be equal to 0, in which case the polynomial will be the constant polynomial fx equal to 1. And this polynomial clearly is not satisfied by any complex number, because no matter what you put in place of x, you will never get 0. So that's why, since we want a polynomial that can be satisfied by a, so k has to be positive. K cannot be 0. And what does that mean? It means that the thing that we were saying right now, that we want to multiply both sides of this final equation by beta naught to the power k minus 1. Since k is positive, k minus 1 is a non-negative integer. It's not negative. So this power of beta naught itself is a positive integer. This power of beta naught is itself a positive integer. It's not a fraction. This implies beta naught to the power k minus 1 times beta m minus 1a. For the sake of clarity, let's introduce some more terms. M minus 2 a square, and towards that end also we write one extra term, beta 2 a to the power k minus 2 plus beta 1 a to the power k minus 1 plus beta naught a to the power k. This is equal to 0. which implies, okay, now we will carefully write the things. Beta naught to the power k minus 1 beta m, this is one term, plus beta m minus 1 times beta naught to the power k minus 2 times beta naught a. Okay, because these two things will give us beta naught to the power k minus 1. So we have split this into two parts and kept them with separate things, one with beta m minus 1 and the other with a. Then the next term, this one, here we will write beta m minus 2 beta naught to the power k minus 3 times, in this term we have a square, so we will have beta naught square a square, which can be written as beta naught a square. And it continues like this. What happens in this term? Beta 2 times beta naught to the power k minus 2. So we already have k minus 1. So only beta naught will be left. And beta naught a to the power k minus 1. Wait. Not this term, of course, the previous one, beta naught, beta 2 times beta naught and beta naught times a to the power k minus 2. So that a to the power k minus 2 we have here, beta 2 we have here, and beta naught to the power k minus 2 and beta naught give us beta naught to the power k minus 1, by which we are multiplying. Okay, so this term is okay. Then this one here, since we are multiplying by beta naught to the power k minus 1, so nothing remains outside. In this case, full beta naught to the power k minus 1 is utilized. And besides beta naught to the power k minus 1, here we have one extra beta naught. So those two things will give us beta naught to the power k. Combine that with a to the power k, you have this. Note that this, then beta m minus 1 beta naught to the power k minus 2, then this one beta m minus 2 beta naught to the power k minus 3, etc. Then this term beta naught beta 2 beta naught, then beta 1 are all integers. Is there any doubt in that these are integers? Of course, there is no problem with the base numbers, beta naught, beta m, m minus 1, m minus 2, etc. But what about the exponents? We just have the fact that k is a positive integer. Is it possible for some of these intermediate exponents to be negative? Actually, that is not possible. You see, you may be thinking that if k is, for example, 2, then there is no problem with k minus 1 and k minus 2. They are non-negative. But k minus 3 is negative, and that says that this may not be an integer, because if k minus 3 is negative, in fact k minus 3 in that case will be minus 1. So this will be this divided by beta naught, and unless we have the condition that beta naught divides this integer, this is not an integer. However, that case does not occur. Why? Let us see. If k is equal to 2, then you can see that if k is 2, then in the original this equation that we have multiplied by beta naught to the power k minus 1, what will this equation look like? I have again brought m. No, I don't know why I am doing this. Where is m coming from? M is nowhere. This should be k. No? K minus 1. And when this is 1, when this is k minus 1, this is k minus 1. When this is 1, this is k minus 1. When this is 0, this is k minus 0. Okay, so it will be, all of this will be k. Sorry about this. I don't know why I keep writing m. These are all k. Okay, so this will also be k, k minus 1, k minus 2, k, and that's all. So that means this is k. Okay, so what were we saying? When k is 2, what happens to this equation? This equation then becomes beta 2 plus beta 1 a plus beta naught k square equal to 0. So after we multiply by beta naught to the power k minus 1, which in this case will be beta naught, because k is 2, so k minus 1 is 1. So after multiplying both sides by beta naught, we get this beta naught beta 2 plus beta 1 beta naught a plus beta naught a whole square equal to 0. That's what this final equation looks like when k is 2. You may not see many terms here. I think it will be better if we take a higher value of k and then see what happens. Say k is equal to 4. Then our original equation will look like, before multiplication, beta 4 plus beta 3a plus beta 2a square plus beta 1 a cube plus beta naught a to the power 4 equal to 0, and then we will multiply both sides by beta naught square because sorry, not square but cube, because k is 4. So multiplying both sides by beta naught cube and arranging things like how we have arranged here, we would get beta naught cube beta 4 plus beta 3 beta naught square beta naught a. We have split beta naught into two parts so that we can get beta naught a. The aim is to get powers of beta naught a. In this case, we will use one beta naught more on this side so that we get beta naught square a square. So beta naught a whole square. Here we will use full beta naught cube. So beta 1 beta naught a whole cube, and here we have extra beta naught, so beta naught a whole to the power 4 equal to 0. So you see that although some of the exponents look like they may be negative, but actually not, that's not the case. The exponents of beta naught that we are getting in this expression, in this special case or in here, you can see that they are in fact all non-negative. Here we have 1, here we have 0, here also we have 0, here we have 3, 2, 1 and 0, 0. So the exponents are all non-negative and the bases are all integers. So all these coefficients are integers. This is now justified. Now look at the final equation. That is beta naught a satisfies the polynomial this one, beta naught to the power k minus 1 beta k plus beta k minus 1 beta naught to the power k minus 2x plus beta k minus 2 beta naught to the power k minus 3 x square etc. plus beta naught beta 2 x to the power k minus 2 plus beta 1 x to the power k minus 1 plus x to the power k. It's a non-zero polynomial because this coefficient is 1, and the important point now is that it's a polynomial with integer coefficients. Thus beta naught a is an algebraic integer. So the positive integer n that we were talking about in the statement of the exercise, so that if you multiply a by n you get an algebraic integer. That positive integer in this case is beta naught. See, these are all integers and beta naught is positive. So that's just it. This completes the solution. So what have we learned here? We have learned that if we have an algebraic number which is a complex number that satisfies a non-zero polynomial equation with rational coefficients, then one can multiply that algebraic number by some positive integer such that the product is an algebraic integer, a complex number that satisfies. Note that this is not an integer, it's an algebraic integer, so that means it's a complex number that satisfies a polynomial, a non-zero polynomial with integer coefficients. Okay, so that is our 10th exercise. Then if the rational number r is also an algebraic integer. Prove that r must be an ordinary integer. Okay, now we have a not just any complex number but a rational number, and it is given that the rational number is an algebraic integer. Note that every rational number is an algebraic number trivially. Why? Because if you take a rational number r, then this rational number satisfies this rational polynomial, which is a non-zero monic polynomial with rational coefficients. So every rational number is an algebraic number. But now our rational number is not just an algebraic number, it's an algebraic integer. Then we have to prove that the rational number must itself be an integer. We can first of all settle the trivial case in which the rational number is 0, because that is already an integer. Since the rational number 0 is an integer, we assume without loss of generality that R is a non-zero rational number. Being rational, R will be the quotient of two integers. Let okay, so now we are going to let R be of the form m by n, where m and n are non-zero integers. N, of course, always has to be non-zero. Non-zeroness of m is needed to make R non-zero, and we can assume n to be positive. If the original rational number R is negative, then the negativity is m will take care of the negativity, and the greatest common divisor of m and n is 1, that is, they are relatively prime. If you have any rational number which has been written as a quotient of two integers, you can always cancel, and especially if the rational number is non-zero, so that these integers m and n are themselves non-zero, you can cancel the common factors. Whatever you are left with, that will be a quotient where the numerator and denominator are relatively prime. Okay, now we use the fact that R is an algebraic integer. Since there exists a polynomial x to the power of, we already have used m and n, so let us take k plus alpha 1 x to the power k minus 1, etc., plus, let us take one extra term, alpha k minus 1 x plus alpha k. Don't forget, not just rational number, but not just algebraic number, R is an algebraic integer. So this is a polynomial in the polynomial ring over the ring of integers. Such that R to the power k plus alpha 1, that means all these alphas are themselves integers. This is equal to 0. This implies, use the expression for R m to the power k divided by n to the power k plus alpha this and so on plus alpha k minus 1 m divided by n plus alpha k equal to 0, or if we multiply throughout by n to the power k, then we get m to the power k plus alpha 1 n m to the power k minus 1 plus etc. plus alpha k minus 1, since we are dividing by n to the power k, so n to the power k minus 1, no, not dividing by n to the power k, multiplying by n to the power k, plus alpha k n to the power k is equal to 0, or we can keep m to the power k on one side of this equation and take all the things on the other side. M minus alpha k n to the power k. Okay, now suppose note that according to our hypothesis, n is a positive integer, so either it is 1 or greater than 1. Suppose it is greater than 1, because n is an integer greater than 1, so by the fundamental theorem of arithmetic, n will have a prime divisor. Then by the fundamental theorem of arithmetic, n has a prime divisor p. Then p divides this, because in this sum every term has n, starting from here n, then in the next one we will have n square, and the exponent of n increases all the way up to n to the power k, and k itself is a positive integer. So p divides minus alpha 1 n this minus alpha k minus 1 n to the power k minus 1 times n minus alpha k n to the power k, that is, but this is m to the power k. This implies by an elementary property of primes that when a prime divides a product of some integers, then it divides at least one of the integers. In this product, all the factors are m. So since p divides this product, so p divides at least one of the factors, which is m. So this implies p divides m. So now p is a common divisor of both n and m. So the greatest common divisor of m and n cannot be 1. It has to be something greater than p. So this is a contradiction to the hypothesis that m and n are relatively prime. So our supposition is wrong. That is, we must have n equal to 1. N cannot be greater than 1, but n is forced to be positive, so that is the only possibility. N must be equal to 1. But then our rational number r is just m, and this is an ordinary integer. So this completes the solution. Then if a is an algebraic integer and m is an ordinary integer, prove this following two statements. Part A plus n is an algebraic integer. Ink is needed. And like that, am is also an algebraic integer, or rather in a same thing. Okay, so now a is an algebraic integer and m is an ordinary integer. Part B is easier than part A. Since a is an algebraic integer, there exists a polynomial. N is not involved, right? There exists a polynomial with integer coefficients such that A satisfies this polynomial. This implies we write the a part in this polynomial somewhat differently. In place of a, we write a plus m minus m. Okay, now what happens if one expands these powers using the binomial theorem, where in the expansion we are going to have terms that contain powers of a plus m and powers of m. Just think of this. You do the expansion. Of course, we will get powers of a plus m, different types of powers of a plus m, and we will also get powers of m. Now, m is an integer. So, powers of m, since we will be dealing with non-negative integral powers of m, so the powers themselves will be integers, and we will multiply such expansions by these integers alpha i's. So after rearranging everything nicely, we will get an expression like this. Binomial theorem and regrouping terms we arrive at a relation that looks like this: alpha plus m whole to the power n plus beta 1 alpha plus m whole to the power n minus 1 and so on, plus beta n minus 1 alpha plus m plus beta n equal to 0. We don't know what these betas are, but we know for sure that since m is an integer and all the alpha i's are integers, these beta i's are also going to be some integers. Note one more thing, that when you expand, in the first expansion you will get the first term as, oh sorry, this is not alpha, what am I writing, a plus m. The first term will be a plus m whole to the power n, and that term is accompanied by nothing, 1. Then of course the lower powers of a plus m will occur, and lower powers of a plus m are available here also. So you may get two terms or several terms involving, for example, a plus m whole to the power n minus 1. So you have to regroup those terms, and the coefficients of those individual terms will be added together to give you beta 1. Like that the other parts will be calculated. Ultimately you will end up with something like this, but keep in mind, because we are dealing with general algebraic systems, so we should see whether using binomial theorem is justified. Where are we right now? We are in, all these calculations are happening where? In the field of complex numbers, because after all this a is an algebraic integer. By definition it's a complex number that satisfies so and so conditions, and in the system of complex numbers binomial theorem is true. So we have got this where beta 1 beta 2 etc. beta n minus 1 and beta n are integers. Thus a plus m satisfies the polynomial hence a plus m is an algebraic integer. So that is part A. In part B, things are easier because we don't have to deal with plus. We already have the equation, this equation. From part A. This implies, okay, now we want MA. So we will multiply both sides of this equation by m to the power n. And which in turn implies ma to the power n plus alpha 1 m ma to the power n minus 1 etc. plus alpha n minus 1 m to the power n minus 1 times ma plus alpha n m to the power n equal to 0. Thus ma satisfies the polynomial x to the power n plus alpha 1 m x to the power n minus 1 etc. plus alpha n minus 1 m to the power n minus 1 x plus alpha n m to the power n in the ring of integers, in the polynomial ring over the ring of integers, because these coefficients are all integers. Thus ma is an algebraic integer. So this completes the current solution. Then exercise 13. if alpha is an algebraic integer, satisfying this equation alpha cube plus alpha plus 1 equal to 0 and beta is an algebraic integer satisfying beta square plus beta minus 3 equal to 0. Prove that both alpha plus beta and alpha beta are algebraic integers. Okay, so you can see that these are or rather these suggest polynomials with integer coefficients that these complex numbers satisfy, namely x cube plus x plus 1 and the other one is x square plus x minus 3. So alpha and beta are algebraic integers. From this information you have to be able to find integer polynomials that alpha plus beta and alpha beta satisfy. That would prove that these two numbers are algebraic integers. Now it will be a very nice exercise to be able to actually find some such polynomials. I tried it, I was unable to find some explicit polynomials that alpha plus beta and alpha beta will satisfy. Maybe I did not try hard enough. Another way of trying to guess what those polynomials might be is to actually find the values of these complex numbers alpha and beta by solving these cubic and these quadratic equations. It will be I think that's how one should be able to guess what those polynomials will be, which are having integer coefficients and which one of them will be satisfied by alpha plus beta and another of them will be satisfied by alpha beta, or by manipulating, the most clever way of solving this exercise will be by manipulating these equations themselves, doing something to them, some operations on them and combining things in such a way that you end up with an equation that is an integer polynomial in alpha plus beta and another one such in alpha beta. Okay, so that way one can tackle this problem, but it's not that we will leave it unsolved. It's a direct consequence of a much more difficult problem, that is the next exercise. So instead of, I suggest you try this solution, try to solve this the way I have said right now, but in place of an actual solution we are going to write this. It follows from the next exercise, and the next exercise is supposed to be extremely difficult because It's a starred exercise, that too with two stars, two asterisks. Usually, this type of exercises in Herstein need some idea that is from outside of ring theory itself. I mean, outside of the, oh, we are doing fields, no, outside of the field theory itself, something related, but which you will not, it's unlikely you will get that idea in some form in this chapter itself. You have to bring something from outside, and that is the case here. So this we will solve, but unfortunately you won't exactly understand the solution because it uses the notion of modules and finitely generated modules. We have not got to that part yet. We are only doing vector spaces. We haven't even completed the first section in vector spaces. Towards the end of vector space theory, there is a small section which says something about modules. Modules, roughly speaking, are systems which look just like vector spaces. That is, in a module, also like a vector space, there is an abelian group under some operation that we call addition, but the scalars that are involved are not coming from a field, not necessarily a field, but from any ring. Okay, so unlike finite dimensional vector spaces, I am saying these things prematurely because we haven't seen what dimension of a vector space is when it is finite. Those things we haven't seen yet, but I am just simply saying, if you already are familiar with these things, just like you have the concept of a finite dimensional vector space, you have the concept of a finitely generated module. Anyway, let's see the exercise first. Part A. Prove that the sum of two algebraic integers is an algebraic integer. So from this part A, it follows that the sum of these two particular algebraic integers, alpha and beta, is also an algebraic integer. So the solution we are going to write now of this exercise 14, we won't understand it, but we will have to come back to it when we finish seeing module theory, or whatever little we have of modules in this book. And part B, prove that the product of two algebraic integers is an algebraic integer. That's why the things have to be seen in the natural order in which they are given in the book. I am not blaming you for asking me to show the other parts prematurely, because you need these things, but just saying that if one says starts with group theory and then one goes to ring theory, in this book at least in topics in algebra, and then one gets to vector spaces and modules and then to fields, then you don't have to keep things hanging like this. Solution A and B we will solve together. And the things go like this. Let us just simply see, and later when the time is right we will come back to it and understand it. Let alpha be a complex number and R be a subring of the field of complex numbers containing the unit element 1. For these two things we define a set R alpha to be the set of all F alphas where fx is a polynomial in Rx. That means, here we have to write equal to. R alpha denotes the set of all complex numbers that are obtained by evaluating polynomials over this ring R at alpha. Or in other words, R alpha is the collection of all complex numbers that can be expressed as polynomials in alpha with coefficients from R. Okay, and alpha is a complex number and R is any subring of the field of complex numbers containing 1. For example, in place of R, one can take the ring of integers. It's a subring of the ring of complex numbers. Of course, the ring of complex numbers is a field, fine, but after all it's a ring, so it will have subrings, and the ring of ordinary integers is a subring of C which contains 1. So in place of R you can think of Z, the ring of integers, or the rational numbers, or even the real numbers, or in fact you can take C itself. Okay, now it's easy to show that R alpha itself is a subring of C, and this is not difficult at all. It's something you can show now itself. But something more is true. In fact, R alpha is the smallest subring of C containing R and alpha. Does it look familiar? it should look familiar because we have got this type of thing in the very beginning of this chapter. There we considered not smallest subring but smallest subfield, that is field obtained by adjoining an element to a given subfield. That idea, but ring version. This also can be shown. So now from here things are somewhat unknown. So R alpha is an R module, and R module is a vector space like structure where this is the set of, this is an abelian group under addition, and the scalars are coming from the ring R. All the other parts of the definition of a vector space are also there in the definition of a module. So this is the set of, we won't say vectors, but things that behave like vectors, and this is the set of scalars, ring elements. So this is an R module. Okay, now we are going to define something called a complex number an algebraic R integer called a complex number an algebraic R integer if it satisfies a non-zero polynomial. Is the non-zero condition there? If it satisfies a monic polynomial, means non-zero polynomial. If it satisfies a monic polynomial in Rx, and the reason for this name algebraic R integer is almost clear. We have already seen algebraic integers. This is a generalization of that concept. So we write, note that an algebraic Z integer is nothing but an algebraic integer. So an algebraic integer is a complex number that satisfies a monic polynomial with integer coefficients. An algebraic R integer is a complex number that satisfies a monic polynomial with coefficients coming from R. And in place of this R, if you have Z or Z, then you get, then algebraic Z integer becomes algebraic integer. Okay, now we make a claim about these things. We claim that R alpha is a finitely generated R module if and only if alpha is an algebraic R integer. Do you see the similarity of this claim to something that we have already got? If F is a field and K is an extension of F, and say A is an element of K, then the degree of Fa over F is finite if and only if A is algebraic over F. Just like that. Of course, here we have the concept of dimension, which in this case we are calling degree. In this case, that concept is finitely generated. We will also attach some number. It will be called the rank of a module, but there are differences, okay, between the theory of dimensions and the theory of finite dimensional vector spaces and the theory of finitely generated R modules. So the results look almost similar. This is finite if and only if A is algebraic over F. This is finitely generated if and only if alpha is an algebraic R integer. We are now going to prove this claim. Okay. And the proof goes like this. First, assume that R alpha is finitely generated. Those of you who already know about a set in a vector space, generating the set, or generating the vector space or spanning the vector space, to them this will make sense. Finitely generated means every element in R alpha can be written as a linear combination of a finite number of elements from R alpha which are fixed. So we write along with this generated with, and such elements in this case are called generators. With generators, since the generators have to come from here, so they will look like this. Some polynomials over R evaluated at alpha, because that's the definition of R alpha. Fn okay. Since there are finitely many polynomials involved, so each one has degree, and Oh, we are saying each one has degree. There is one polynomial which has no degree, that is the zero polynomial. If we carelessly take these fi's, is it possible that one of them is the zero polynomial? If one of these fi's is the zero polynomial, then that fi alpha will be 0, and from a set of generators you can always remove 0. Why? Because 0 actually does not help us in generating anything other than 0. It's like in a vector space having a set of vectors like this. Say it has 3 vectors, 2 of which are non-zero, v1 and v2, and you have 0. The subspace, I am prematurely saying these things, okay, so just simply bear with me. The subspace, because anyway we have to come back to this solution to properly understand it when we have finished, will have finished the things on module. So if we have a subset in a vector space like this, where v1 and v2 are non-zero, then the space that this set spans in the vector space can also be obtained by just considering these two vectors. This does not contribute anything to the span. Presence of 0 or absence of it, that does not matter at all. So like that, we won't have a 0 polynomial. In fact, but we should mention that minus 0. And so in particular, since these elements are supposed to not be 0, in particular no fi is the 0 polynomial. So each one has degree, and we can take k to be the maximum of the degrees. Then it's easy to see that these elements alpha to the power k also generate R alpha. Why? Because since each one of these things is a polynomial expression in alpha, so if you multiply all these, each one of them by some element from R, some ring element, then ultimately you will get what? A linear combination of powers of alpha, where the highest power available of alpha will come from the highest degree of these polynomials. There you will have alpha to the power k, so it will go till this. After that, I mean, still higher powers of alpha are not available. So these themselves will generate R alpha. R alpha as well. But this then implies what? This particular element alpha to the power k plus 1 will also be generated by these powers of alpha, lower powers of alpha, with coefficients coming from capital R. So this can be written as n naught plus n1 alpha etc. plus nk alpha to the power k. Nk belonging to R. But then alpha satisfies the monic polynomial x to the power k plus 1 minus let us write it systematically, nk x to the power k etc. minus n1 x minus n naught belonging to Rx. Okay, alpha satisfies this monic polynomial over R. But that just is the definition of an element becoming an algebraic R integer. So alpha is an algebraic R integer. So we have proved one half of our claim. Conversely, assume that alpha is an algebraic R integer. Then alpha will satisfy a polynomial like that. Then alpha to the power m plus a1 alpha to the power m minus 1 etc. plus am equal to 0 for some this belonging to R. Okay. And for some positive integer, let's mention that also, positive integer m. This is the consequence of alpha being an algebraic R integer. And hence, using this repeatedly, if necessary, we see that any element in or any element of R alpha can be written as a linear combination of this with coefficients from R. Why n minus 1, or not n minus 1 but m minus 1, sorry. The reason for having m minus 1 here and not m is because you can see that alpha to the power m itself is a linear combination of the lower integral powers of alpha. So in any combination, or rather in any element of R alpha, elements of R alpha look like what? They are polynomial expressions in alpha. So they will look like some like this, say gamma naught plus gamma 1 alpha etc, gamma, say L alpha to the power L. Now if this L is really quite large, then in place of L you can put, how should I explain this? Say in place of L you have M, okay, then this alpha to the power M, you can, in its place you can write minus a1 alpha to the power m minus 1 minus etc minus am, and then you rearrange the terms. You will see that f alpha is a linear combination of these powers of alpha only. If you have still higher term, you have to use it one more time. So that's why we have written using this repeatedly if necessary. We see that any element in R alpha can be written as a linear combination of these powers of alpha with coefficients from R. The coefficients gamma naught, gamma 1, they are of course coming from R. Now what is the implication of this? The implication of this is this. This implies one alpha, alpha square, etc. is generate R alpha. Thus, R alpha is a finitely generated R module is a finitely generated R module. So we have proved our claim that we wanted to prove. Now we will use these things to get our job done. Now let gamma 1 and gamma 2 be two algebraic integers. Our aim is to show that their sum and product are both algebraic integers. Now from what we have done in the previous paragraph, algebraic integers means algebraic z integers or algebraic z integers. Since gamma 1 is an algebraic integer, this is a finitely generated C module. Like that, since gamma 2 is an algebraic integer, this thing is a finitely generated C gamma 1 module. So here we are using the fact that gamma 1 and gamma 2 are algebraic integers to draw these conclusions, and in these conclusions we have of course we are using what we have proved in the previous paragraph, but note one more thing, that this is R, this is a ring, and this is also a ring. Okay, let me just see. I am having a slight confusion in this. What is R? R is a subring of the ring of complex numbers that contains 1. And the way we have defined R alpha is, again we have mentioned it also, a subring of the ring of complex numbers, and clearly it contains R and hence it contains 1. So this is a subring of the ring of complex numbers containing 1. This is also a subring of the ring of complex numbers containing 1. So in place of R, to form R something within square brackets, we need subrings of complex numbers. So both these subrings can be used. Okay, but there is one subtle point which if one is not looking carefully, they will miss. Gamma 1 is an algebraic integer means what? Gamma 1 is an algebraic Z integer. That is, gamma 1 satisfies a monic polynomial with integer coefficients. Now, it is given that gamma 2 is an algebraic integer. That means gamma 2 is an algebraic z integer. But what tells me that gamma 2 is an algebraic z gamma 1 integer? Because if that is not the case, then how am I drawing this conclusion that this is finitely generated? This implies this. Why? Because you see, z itself is contained in this subring. So the fact that gamma 2 is an algebraic integer means gamma 2 satisfies a monic polynomial with integer coefficients. Now such a polynomial, since they have integer coefficients, those coefficients are also here, and that tells us that gamma 2 is an algebraic z gamma 1 integer as well. And that's why, in fact, to make matters more clear, let's include this is an algebraic integer, and hence an algebraic z gamma 1 integer. Yeah, now we can conclude. This is a finitely generated z gamma 1 module. Okay, now from these two things one can prove that this is a finitely generated z module. How? For that, you see the proof of theorem 511, where we proved that a finite extension of a finite extension is a finite extension. It has the same flavor, and if you look carefully, you can see that almost there is nothing to do. That the proof of theorem 511 tells us, in fact, that one gets the proof of this fact almost similarly. You don't have to make many changes. Okay, so now we have got a very useful fact that this is a finitely generated Z module. Since this complicated looking module contains the ring of integers gamma 1 and gamma 2, we see that it contains this C module, and it also contains this C module. To see why, you don't forget that this is not just a C module, but this is in fact the smallest can we say like that, R alpha. This is no, not module. This is the smallest subring containing both C gamma 1 and gamma 2, and the thing inside itself is the smallest subring containing both C and gamma 2. That's why this contains C and gamma 1 and gamma 2. Now, since this whole thing is after all a subring of C, so it will contain gamma 1 plus gamma 2. Now, this one, C gamma 1 plus gamma 2, is by definition the smallest subring of C containing both C and gamma 1 plus gamma 2, and this is just some subring containing both C and gamma 1 plus gamma 2. So naturally this one will be contained in this, similarly this one. Now this is a finitely generated Z module, and these are contained in this. So they also will be finitely generated Z modules. Thus, so again, but by what we proved in the previous paragraph, gamma 1 plus gamma 2 and gamma 1 gamma 2 are both what is the term, I forgot that, algebraic Z integer, in other words algebraic integers. Thus so this completes the solution. I think we have got the gist of the solution. We somehow in a vague manner we understand the solution, provided we are familiar with those parts of vector space theory which have the notions of linear combinations, span, those things, dimension. We will come back to it. And finally, there is this last exercise. It's the first part of this is a numerical one, and using it we can prove the second part. A. prove that sine 1 degree is an algebraic number, not an algebraic integer, an algebraic number. We have to prove that. From part A, prove that sine m degree is an algebraic number for any integer m. Okay, so we begin part A by noting some numerical facts. Note that these are coming from standard trigonometric identities. 1 minus 2 sine square 15 degree. 1 minus 2 sine square theta is cos 2 theta. So cos 30 degree is cos 30 degree 1 minus sine square 15 degree is, that means, what the hell, I have made a mistake here. 1 minus 2 sine square theta is cos 2 theta, not sine 2 theta. So this is square root of 3 divided by 2. This mistake will change the calculations entirely. Okay, so I will do one thing. Let me tell you the strategy of this exercise. We start from 15 degree. We somehow use this relation. So we have got a relation involving sine 15 degree, and I wanted rational numbers, but here I am getting an irrational number, so this will not work. Then what I did, I wrote sine 15 degree in terms of sine 5 degree, because sine 15 degree is sine 3 times 5 degree, so we can use the formula for sine 3 theta. And then I used sine 5 degree to write an expression involving sine 1 degree, because that is sine 5 theta, which also has an identity that expresses it as an expression involving powers of sine theta. Then these relations were used to show that a polynomial with rational coefficients is satisfied by sine 1 degree, and hence sine 1 degree will be an algebraic number. One can similarly prove that cos 1 degree is an algebraic number. Then for the second part, one can use induction on m. For negative values of m, we don't have to do anything separately, because if m is negative, then sine m degree is minus sine minus m degree, and if m is negative, then cos m degree is cos minus m degree. So one can use these two things, and the fact that sine 0 degree and cos 0 degree are both integers and hence algebraic numbers, one can then proceed to prove that sine m degree and cos m degree. We have to take the help of cos also simultaneously, because we would be using addition formula for the trigonometric functions to do our induction proof. So then one can prove that sine m degree and cos m degree are both algebraic for any positive integer m by induction on m. But here, because of my carelessness, I thought it is sine 30 degree, thereby getting 1 by 2. So this is not true, but I have told you how to approach for the solution. So this one remains incomplete. We will complete it in the next video on field theory, and then we will also start the next section, where I think we have to show, if I am remembering it correctly, that the familiar number e from real analysis, which is the sum of this convergent series, we have to show that this is a transcendental number. It's not an algebraic number. So this will settle the question of whether transcendental numbers exist or not. That section is just about that. So it's a little, it uses ideas from analysis or elementary calculus actually. The deepest result we will need in the proof of this fact is Lagrange's mean value theorem from real analysis. So we will see those things. So let me end this video here itself. I hoped to complete it today, but unfortunately I don't want to now struggle with this here. Instead, I will rectify the solution and we'll come back in the next video. So that will be all for tonight, and tomorrow we have what? Oh, group theory exercises from Galilean. Okay, so until then, it's me, Lucifer, from a mathematical room. Have a nice night.